Yeah. All right. So in the video we just watched, at the end or in the initial try, I'm gonna draw a vase. Okay. I think the vase is the easiest to see. Thanks, Rex.
It's a beautiful thing. I like the flower. Very creative.
Okay. Whoa. All right. That's the bottom. It's the stem of the vase. You know, so it looks a little more fancy. It's kind of on a pedestal. Okay. So now that vase is sitting on a tablecloth, right?
Sure.
Okay. Now in the video, the tablecloth is pulled which way?
The positive direction.
Okay, it doesn't matter. We can say it's pulled that way. Okay. Does that work?
Yeah.
So in order to pull a tablecloth, they apply a force to the tablecloth. So there's a force in this direction. Okay. Now before that tablecloth was pulled, this vase had what force directing on? Which forces?
Gravity.
Gravity down and
Tablecloth.
normal up. Right? Now Newton's first law says that object will stay at rest as long as no outside forces are applied, right?
Correct.
But once that tablecloth is pulled, there is another force applied. What's that force? Friction. Which way does friction act on the vase?
To the right. Opposite way.
Left.
Okay.
Down.
Does the friction act in the same direction as the tablecloth or opposite direction? Okay. Well, think about this. Which way does the vase move?
This
To the right.
The vase has it starts out with an initial velocity of 0, right?
Yeah.
Right? And then it ends with a velocity in that direction, doesn't it? So just based on that alone, which way do you guys think the vase is accelerating? To the right or to the left? To the right. In order for this to happen, from 0 to go to here, we need to have an acceleration to the right. Does that make sense? Guys, does that make sense?
Yes.
Yeah.
So if the acceleration is to the right, which way is the force applied? Okay. Think about it this way. When you're on the playground, the force of friction. Okay? Think about this. When you're on the playground, right, Jose?
Right.
Okay, when you're a mean little kid and you're pushing other kids around, right? Okay, you're still a mean little kid, right? All right. Now, when you push somebody, if I push somebody to the right, I apply a force to the right. Which way do they move?
To the right.
Do they move in the direction I apply a force or the opposite direction? The direction I apply the force, right? So when you were a mean little kid in 3rd grade and you're pushing kids down, you push them to the right, they go to the right. Okay? I know. It's my right. Better? Okay. So you push to the right, they go to the right, don't they? So if this is going to the right, which way is the force applied?
Right. Straight.
Those that are saying left, how does that agree with you pushing kids?
But the friction is
It doesn't
going
agree.
the other way, isn't it?
Ah, but think about forces and accelerations, right?
Force is going to the right too.
Friction is just like any other force. Now you're used to the definition of friction where it opposes motion, right? Okay? If I think about this in the whole tablecloth, just looking at the tablecloth, not anything else going on, right? Right? The tablecloth wants to keep the vase in the same spot.
Right.
Right? The tablecloth is moving this way. It wants to stop the vase from going that way. Right? So which way is the friction point?
To the right.
To the right. The force of friction from the tablecloth points to the right. The reason being is that whole reason with when I push somebody, and I'm not condoning pushing or bullying in any case or whatever, okay? But when you push something or somebody, it goes in the direction you push it, doesn't it?
Yeah.
It accelerates in the direction you push it. Right? If I push my chair that way, right? It goes that way.
Stop pushing stuff.
Doesn't it?
Yeah, I just noticed.
Okay. What's that?
Okay, you know how they pull the tablecloth?
Yep.
They obviously have to like pull it up a little bit so it makes the things fall. What if you pull it down?
If you pull it down, that might work a little better.
Yeah, it would just keep the things in place. You know, you pull it down.
So maybe they could have a pulley in the bottom and pull.
Yeah.
That'd be a good idea. Maybe we should write them a letter and see if they can try it again.
Right on the ladder.
I'll see if I can find their emails on Discovery Channel. But I wonder if that would work.
I
Okay.
know, because the things will keep it will keep the things in place. Gravity will keep it in place, and you just pull the thing down.
That'd be a good idea. Do you have a motorcycle?
Huh?
I do.
Do you have a motorcycle?
I do.
Rex, you do?
I do too. I got two.
I don't know if I can allow you to go speed to 100 miles an hour though for school's sake.
Oh no, I could.
No.
I think it'd be okay.
I got a muscle.
Danielle, we'll see if we can. I don't know.
Right.
I kind of want to try that too.
I know, it would just work for
It's
It would.
I know
for
it's gonna work
educational
fine.
purposes. though.
Yeah, let Rex risk his life for educational purposes.
You're not right.
It's right, guys. We're gonna get on the roof and we're gonna climb out the window to get on the roof because it's for educational purposes. That's okay. No. All right. So back to this. I'm not about getting views. I'm about teaching you guys. All right. So. Okay, back to this.
You get money.
So does this make sense, guys? If the outside force is in that direction, or sorry, since we accelerate in that direction, that means the outside force has to be in that direction. Does that make sense, guys? Okay, does that make sense?
Yes.
These two directions right here?
Yeah.
Okay. So, relying on your knowledge from your childhood and other things, accelerations and forces that are applied, are they in the same direction or opposite directions? Same. In the same direction. Okay. Now, how does the acceleration relate to the force applied? If I apply more force, do I get more acceleration or less? More. Okay. What about if I have bigger objects? Okay. Let's say I'm pushing this. Let's say I'm trying to move the sofa in the chair out of the living room. Right? Which one's easier to move?
Chair. I mean, chair.
The chair, because it has less mass, right? So if I apply the same force to the sofa and to the chair, which one moves more? The chair, because it has less mass. So acceleration, right? How's it related to mass? You guys just said more mass had less motion, right? Right? So acceleration and mass are inverse. What about force and acceleration? What about force and acceleration? Direct. So based on your previous experiments in physics, even though you didn't know you were experimenting in physics, you were. Okay? You guys are saying acceleration is directly related to force, right? And inversely related to mass. You guys know Newton's second law already. Okay, Kyle, you have a question? No? Okay. So Newton's second law is the acceleration of an object. The acceleration of an object is equal to the sum of all the forces okay. What's sum of all the forces again? What's that called? Net force. Good. So this sum of all the forces, this is really called net force. The acceleration of an object is equal to the sum of all the forces multiplied or divided by the mass? Divided, because it's inverse. Okay? Divided by the mass of the object. Now Newton's first law kind of had a cool sentence that depended on situations. This sentence just sounds more like a what? I know it's a sentence, but it sounds more like an
Equation. Option.
sounds like a what? Someone said it?
I mean, opinion.
Equation.
An equation. Right? This is a math sentence, isn't it? We have equals and divided, right? So how can I write this? Rex, you know how to write the equation?
No, I just have a correction. It's a physics sentence.
Okay. All right, physics sentence. Good, thank you. I appreciate that. So, this physics sentence with math words in it leads to an equation. The equation is
A equals F.
I hate equations.
So now we're finding
Divided by M.
Divided by m. That's exactly what it is. That's Newton's second law. Okay. So, A, is this a vector? Yeah. Is F not a vector?
Yes.
Yes. Is mass a vector? No, mass is a scalar. So, A is acceleration. What units is acceleration in? Meters per second. Very good. F net is net force, and that's in newtons. And M is mass, and that's in Jameer, you need a drink?
I do.
Okay, go ahead.
You thirsty?
Does that make sense? Guys, that make sense?
It sure does.
Okay. Now, I can rewrite this in a different way. Okay, now I'm going to rewrite this where I'm going to solve for F next. I found that in most physics textbooks will show it this way as well. students struggle with the addition and then division. Okay, because it says F net is the sum of all the forces, right? So this F net is really not just one force, but 2, 3, 4, many forces that are all added together. Okay? And a lot of times when we have a division after addition, students will do that incorrectly and they'll just divide the last part of the addition by the m and not the whole thing. Okay? So we can write this in a different way that might be more conducive to successfully completing the calculation. F net equals ma. Now I have all my addition on one side, all my multiplication on the other side. Do all your addition first, then divide if you need to. So either one of these is Newton's second law. And that's why this law, instead of being like the inertial law, is called the equation. That's the nickname for this law. You got real creative on that one. What? Well, the beginnings are the same, Nan, but we're going to get a lot more in depth.
Woo!
Yeah. All right.
Like 20,000 leagues.
Not that many leagues. That's a lot of leagues. Okay. There's a big octopus at the end. It's really scary. All right.
Dolphins lost last night.
Hey, take it easy. So,
To the Buccaneers,
Oh God.
Yeah, one more time.
you get down by a lot. It messes you up really. All right. So, now, there's something very important that we cannot overlook about the force and the acceleration. Okay? Kind of goes back to those playground situations we were describing earlier. What do we know about force and acceleration? No. What did you say, Katrina? They're in the same direction. Okay? Force and acceleration. So F and A are in the same direction. And A are in the same direction. Force and acceleration are always in the same direction. Okay. If you're more of a mathematical mind, think about it this way. Mass is a scalar, right?
Yeah.
Does it have a sign?
Yeah.
So it can never be negative. Mass is always a whole number that's positive, right? Not a whole number, but mass is always a number that's positive, correct?
Sure is.
All right. So if mass is always positive, if my acceleration is positive, can my sign change for my force?
Theoretically.
No, it can't. Because if mass is positive, if my acceleration is positive, my force is going to be positive, right? Positive times a positive is a positive. If acceleration is negative, then my force will be negative, because positive times a negative is always a negative. So force and acceleration are always in the same direction because mass is always a positive number. Okay, does that make sense?
Yeah.
Okay. Are there any questions? Okay. No. Another hypothetical situation.
Wait, what if there's helium in something?
Okay. Okay, here's the front of the car. I know sometimes it's hard to tell my cars if it's the front or the hood or whatever. Okay, yeah.
What if there's like helium in the balloon?
Okay. Then there's that buoyant force. Okay, this is net force, right?
Yeah.
That means it's the sum of all the forces. So if I have a balloon that's going upwards, it has gravity. So here's the balloon. Right? Right? There's gravity acting down. Right? But the helium inside this is less dense than the air on the outside. It's kind of like an ice cube in water. Right? The ice cube is less dense than the water, so it floats. Okay?
So it's like if you put milk in water in one cup and one down.
Or if you put oil in water. Okay, but the oil is lighter than the water too. Okay? So there's something called a buoyant force. Or buoyancy. Michael, be quiet. Okay. So there's a buoyant force that applies upward. Now based on how much this density differs between the helium and the air outside, this buoyant force will either increase or decrease. Okay? If there's pure helium on the inside, then this buoyant force will be a lot greater. If it's helium mixed with normal air on the inside, then it'll be less. Okay? But since that buoyant force is greater, this will move upward, it'll accelerate upward. Okay, and that comes from this net force idea. The net force is the sum of all the forces.
Indubitably.
Okay? So the forces acting are gravity and the buoyant force. Okay, does that make sense?
Yes.
The vectors. Alright, so my car. Back to my car. Let's say the car has a velocity in this direction. Okay?
Put lines.
Has a velocity in that direction. Speed lines? Okay.
Going too fast. Accidentally.
Velocity in that direction, right? Now, there's a red light up ahead. So this person starts to slow down. Okay, the light's already red. It's not turning yellow. Okay, the light's already red. So this person needs to. They do need to accelerate, but which way?
In the opposite direction.
The opposite direction. Okay. So this person should be accelerating that way if there's a red light up ahead, right? Right? Now, Nan, come here. Which way is the force? Don't shout it out, okay? Which way is the force acting in the car? Okay, Kyle, I'll let you answer, okay? But when everybody think about this, okay? Which way is the force acting in the car? Which way is the net force acting in the car? Okay? We thinking about it? Okay, Kyle, so you can answer. Which way? To the right or to the left? Which way is the net force?
Are those equal?
They can be equal. That's fine.
I think it's to the left.
You think it's to the left,
It's to the right.
but you're thinking it's to the left. What'd you say, Reggie?
To the right.
It's to the right. We sure?
Yeah.
So Kyle says left. Reggie says right. Now, what indicates force, guys? Is it velocity or acceleration? Acceleration. So, which way is the acceleration? To the left, right? Gentlemen. Okay. So, the acceleration is to the left, isn't it? If I think about this, let's say the person's braking, right? They're applying their brakes, so their brake lights are going off. Okay? So, their initial velocity might be 50. Their final velocity is hopefully 0, right? Right? So that means their acceleration is 0 minus 50. It is negative. Acceleration is this way, isn't it? Right? And acceleration and force are always in the same direction. So the force is... Okay, that's all right, Reggie. Reggie, that's a common misconception, though. Okay, remember we talked about this the other day. A lot of times students believe that velocity indicates force. Right? They think because something is moving in that direction, it has a force in that direction. Is that the case? No. Remember your homework you guys did the other day? The water pail was coming up at a constant velocity. Constant velocity means 0 acceleration, right? But a lot of you drew your net force vector up. Right? You drew a stronger force going up because the pail was moving up. You guys remember that?
That was a mistake.
Okay, and that was your mistake. Because velocity does not indicate force. What does? Acceleration. So maybe you want to make a little note. I don't care where you make the note. Okay, I'm gonna put it up here. Acceleration indicates. Oh, that's the wrong spot. Indicates force, not velocity. Okay? So the acceleration is what tells us something is experiencing a force, not the velocity. Okay? So if we go back to this vase idea, the reason I would boil it down to the acceleration, and which way the acceleration is because the acceleration tells us the way the net force is acting. Okay, does that make sense?
Yes.
Okay. So this car, even though it's moving this way, is experiencing a force in the opposite direction. Right? The brakes that are being applied to the wheels are applying a force that goes in the opposite direction of the car's movement. Does that make sense?
Yeah,
Only the way you teach it.
Yeah. Only the way I teach it.
that's so nice, right?
You're like making my ego grow. It's wonderful.
But you're making it dream.
Thanks, Katrina, for your sarcasm. I appreciate it. All right. Any questions? Okay. So let's look at this in a situation. A new situation. Here a baseball. Everybody see the baseball? Okay, I'm not gonna throw it to you. All right. Now, if I drop the baseball, okay, what happens?
Catch it.
Falls.
Okay. If I drop the baseball, right? What force are acting on the baseball?
Gravity.
Only gravity? Okay, we can ignore air resistance. Okay.
Your hand.
We have a thin sheet of plastic in between our table, in between our plates and the tablecloth. All right, we can ignore air resistance. All right. That was a joke from the video. You don't have to laugh. All right. So, if I drop the baseball, the only force acting on it is, well, right now my hand in gravity is, right? But once I drop it, just gravity until it's the floor. So, if this is the baseball, right, and it is falling, okay, which way is the acceleration? Down. Oh, those are speed lines. So acceleration is down, right?
Yeah.
What force is acting on the baseball? Gravity.
G.
Force of gravity, right? Does everybody know what the acceleration due to gravity is?
9.8 negative 1 squared.
Okay. So acceleration due to gravity is 9.8 meters per second squared. Now, someone said, isn't that negative, right? Okay. It is only negative if we choose a positive direction. Have we chosen a positive direction yet?
No.
No. Okay. The magnitude of the acceleration due to gravity is 9.8 meters per second squared. All right. Now, if I call down positive, that makes this positive. If I call up positive, that makes this negative. Okay. And that's on Earth. It changes based on whatever planet we're on and our distance from the center of the Earth. Okay. But on the surface of the Earth, it's 9.8 meters per second squared. Does that make sense, guys?
Yeah.
Okay. Now, I want to know, what is the force of gravity exerted on the baseball?
Can you rephrase the question?
How hard does gravity pull on the baseball? Okay. So what is the force of gravity exerted on the baseball? Now, in order to figure out this force, what do we need? Newton's second law says F net equals ma, right?
Yeah.
So we need to know the mass. Now, I'm just going to throw out an arbitrary mass for baseball. I don't actually know the exact mass. We'll just do 1.5 kilograms. Probably a heavy baseball.
Sounds legit.
Okay. It's probably close.
It's a softball.
Okay. It's an object that has a mass of 1.5 kilograms. It appears to have stitches like a baseball. Okay. Might not be an actual baseball. All right. George, with me? Okay. So, if I want to figure out the force of gravity acting on the baseball, I need to look at Newton's second law.
Yeah.
Okay. It tells me that F net equals ma. Right? F net equals mass times acceleration. Okay. Now, which way do you guys want to call it positive? Up. Okay, we can call it positive. So I'll draw it in blue so it sticks out. So up is going to be the positive direction. Okay. So up is the positive direction. Right. So what do I know here? We know that our mass is 1.5 kilograms. We know the acceleration is negative 9.8 meters per second squared because I called up positive, so that acceleration is negative. Right?
Yep.
So, and our force acting on the ball is what? Just gravity, right? F net is negative Fg, right? Right? Why did I put negative Fg? It's going down. Right?
Well, I thought F net equals acceleration times mass.
It does. But F net is also the sum of all the forces acting on the object, right? Right?
Yeah.
F net is not just it's not the answer. F net is the sum of all the forces. Okay? So if I asked you for the net force, then it would just be F net, Kyle, you're right. Okay? But I'm asking for the force of gravity, right? So I need to look at all the forces acting on my object. Now the only force acting on my object is gravity. Okay? So the force of gravity, Fg, is going to be equal to mass times negative 9.8 meters per second squared. Oh, I don't need to write that down. So I plugged in what I knew, right?
Yeah.
Now, you may have noticed I left off this. What did I leave off here? The negative sign. Why do you think I left off that negative sign? Where do we include the negative sign? The negative 9.8, right? I can only include that negative sign once. Okay? This negative FG and that negative 9.8, they are telling me the same thing, aren't they? They're telling me that the force of gravity is down and the acceleration is down, right? Okay? I only want to include that once. And that's one of the big areas where students make mistakes. They'll try to include negative signs multiple times. Okay? So maybe if it's a little easier to swallow, we'll take that negative up there. Does this make sense? Okay. So 1.5 times negative 9.8, what do I get? 14.7. So the force of gravity is negative 14.7 newtons. Nope. And this negative means it is up or down? Down. So that negative tells us the sign. Does that make sense, guys?
Yes.
Yeah.
So if you were to switch from for a positive one, like mean the mass is negative, or that would be.
Nope.
Gravity would be positive.
If I switched which direction was positive,
Yeah.
that means our gravity instead of being negative would be.
Yeah, that's what I meant.
Okay.
Wouldn't it be easier to do that?
What?
Wouldn't it be easier to do that?
In some cases, yes.
Because then you won't have to
Yeah. Okay. Are there any questions? So now this worked to find the force of gravity acting on the baseball, right? What if I wanted to make this more general, Kyle, to just a mass and gravity? How can I switch this equation so it's just a mass and gravity? Well, what was my mass here? 1.5. Which one's gravity? Negative 9.8. So I can make a general equation for the force of gravity. Force of gravity equals m times g. Right? What's g?
Gravity.
What about gravity?
Is it like
G equals 9.8 meters per second.
square?
Okay. So that can be a general equation for the force of gravity. Katrina, does that make sense?
I thought you said one of them had to be negative.
No.
I'm so confused now.
Okay. Because we chose up was positive, right?
Right.
One of these has to be negative. Okay? Now, this is a general equation. Okay? Notice I don't have the vectors on here. Okay? This is the magnitude of the force of gravity. Okay? This one should have a vector. Okay? But that one is the magnitude of the force of gravity. Okay? Now, the direction depends on your situation. If I'm looking at this problem, this force would be positive or negative. Negative, right? Because up is positive, gravity points down. Okay? If I switched it around and chose my positive direction to be down, then this would be a positive force. That's why I didn't write the vectors on it. It's a magnitude. Okay, does that make sense?
Yeah.
Okay. Are there any questions? Any questions about this situation? Kyle, you got a question?
No. Just wait till you do it.
Okay. One more situation. Okay. Now, let's say oh, it's not. It's my hand. I think it's,
Yes.
we'll say it's Jameer's hand. You got a blue fingernail polish on.
That was
Okay. We'll put a
I
big
really
watch.
thought that was like the little log that you sit on.
That's a stick. It's like they playing stick ball.
Just watch.
I thought that was a clock.
Right, watches our clocks. Good job. Okay. So, that hand has caught the baseball. Okay, does that make sense? Sorry, I'm not an art teacher. All right. The hand has caught the baseball. Amani, pay attention, please. All right. I want to know what is the force exerted by the hand. Okay. That's just to show that it was someone's hand. We don't need the watch. What?
Oh, it's a watch.
It's a watch. Okay. We'll erase the watch. All right. So, what's the force exerted by the hand? All right. So, to get started with this, we are going to draw a free body diagram, right? Okay. What? I know this one over here is a free body diagram. But has the situation changed?
I'm talking about, I thought that was a free body diagram.
No, that is a picture.
Isn't that what?
No, a free body diagram shows all the forces acting on an object.
So just draw.
We're going to draw a free body diagram for the baseball. Okay? So what forces are acting on the baseball?
Your hand.
Okay, the hand. Which way is the hand point?
Up.
Up. Okay. What else?
Gravity.
Gravity. Which way is gravity point?
Down.
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 Now, if the baseball has the same mass of 1.5 kilograms, so the mass is still 1.5 kilograms, will that force of gravity change?
Yeah. No.
Will the force of gravity change?
No.
No. So then why does the baseball move or not move?
With the hand.
Because why?
Does it not? It's equal. There's such a
What's-
muscular.
What's true?
Get it.
Say it, Reggie. What'd you say?
It's equal. The forces.
Okay, the forces are equal, right? So by putting my hand here, it doesn't mean that that gravity is no longer acting on the baseball. Gravity still acts on the baseball, right?
Yes, sir.
It's just now there's another force acting, and like Reggie said, those forces are
Equal.
equal. Okay, assuming the acceleration is 0. Okay, if acceleration is 0, then those forces should be equal, right? Now we want to figure out the force in the hand. So where should I start? Well, we know acceleration is 0. Mass is still 1.5 kilograms, right?
Yes, sir.
Right? Now, this next step, guys, we're kind of zoning out a little bit, right? This next step is probably the most important part. Okay? It's the F net part. And like Kyle said earlier, wait, F net should just be a number, right, Kyle? Weren't you thinking that earlier?
I didn't say that.
Okay. I'll watch the tape again. Alright? But F net is not just a number. F net is not the same thing you plug in every time. F net depends on our situation.
It's the hand, right?
It's not just the hand.
It's gravity. Isn't it?
Everything acting on it. Right? Now, which way do you guys want to call positive here? Up? Okay, we can say without being positive. Okay? So that means the net force acting on the hand, or acting on the baseball, is what? It equals 0, right? But what does it equal in terms of the forces? We have the force of the hand, right? Because F net is sum of all the forces, right? Force of the hand, and that's up, so I'm going to leave that as positive, and the force of gravity, which is down. Yep, so it is negative. Okay. Now, for whatever reason, students struggle the most with this part right here. F net equals force hand minus force gravity. Okay. Because students want to do it nonsense, just say, well, F net is 0 because we're not accelerating. And yes, that's true, we are not accelerating, so this F net does equal 0. But it also equals this. And this is how we figure out the force exerted by the hand. Okay. Does that make sense?
Yeah.
Okay. Reggie, or Jimmy, or shake your head no.
Oh, yeah.
Stay with me the whole time, okay? All right. So, we know from Newton's second law that F net equals ma, right? That's Newton's second law. So now I can plug in what I know. This F net is not 0. The 0 will be on this side. Maximum acceleration because acceleration is 0. This F net is what? Force of the hand minus force of gravity. Okay? And then ma, what's m?
1.5.
1.5 times
0.
0.
0.
What's 1.5 times 0?
0.
0. So the force of the hand minus the force of gravity equals 0. Okay. Now what do we know about the force of gravity? It's mass times times acceleration due to gravity, right? So we know the force of the hand minus mg equals 0. Right? Does that make sense? Does that make sense, guys? Okay. So the force of the hand minus mg. Now we can plug numbers in here. What's the mass? 1.5. What's g? Positive or negative? Okay. Resounding negative. Why do we all say negative?
You didn't put a negative.
I know I didn't. Why do we all say negative?
Because up is positive.
Because up is positive and gravity is
Going down.
going down. Right? Up is positive and gravity is going down, right? So we're all saying that gravity, this 9.8 is down. But didn't we already say the force of gravity is down? Up here, we drew a downward arrow, right? So when we plugged in this, F net equals F tan minus Fg, we already said that gravity is negative. So if I put a negative in right here, which is what I've seen tons of students do, if I put a negative in right here, then I'm in essence saying that gravity is which way? Up, because the two negatives will cancel. All right? Do not double count your negatives. Okay? And this is where the whole part of going back and looking at your results and making sure they make sense. If we put a negative in right here, when we solve, we end up with a force of the hand being negative, because we're going to have to subtract the answer over here, right? Which means the force of the hand will be downward. Does that make sense with our picture? Force of the hand being downward, does that make sense with our picture? No, it doesn't. Okay?
It does.
So that means we'd have to make an error along the way. What's 1.5 times 9.8?
A number.
14.7, good. So force of the hand minus 14.7 equals 0, right? Simple algebra. Right, following? You okay? Simple algebra, add 14.7 to both sides, right, Locke and Skylar? Add 14.7 to both sides, what do we get? Okay, we know the force from the hand is 14.7. And since that's positive, that means it's upward. Okay. Does that make sense?
Yes.
Okay. Any questions?
No, sir.
No questions?
No.